It's electric.
You can see it.
It's electric.
You gotta feel it.
It's electric.
Woo, shocking.
It's electric.
She's a boogie, got the time. She's a boogie, got the time.
She shot the boogie.
You can know it.
It's electric.
Boogie, boogie, boogie. And you can hold it.
It's electric.
Boogie, boogie, boogie. But you know it's there. Here, there, and everywhere. I've got to move. I'm going on a party ride. I've got to groove.
I know you were disappointed that I didn't have any music for you the last couple of videos, so I had to give you a little electric side because we're going to talk about electricity in this video, and you can follow along on page 322. Let's begin. Alright, let's get rolling. You can see from this graphic that we have here on the PowerPoint that there's going to be a couple videos for you to see about cogeneration. But let's talk about these other terms that are here. And it starts with something called energy carrier. See, electricity is an energy carrier. It's something that moves energy and delivers it in a convenient, usable form. And that usable form, of course, gets to the end user, which is you and me when we plug something in. Electricity has found itself to be very convenient. And when we make electricity, we'll see the different energy conversions that happen in order to make electricity happen. What is electricity? The easiest way for you to remember what electricity is to see the elect. These are electrons in motion. Electricity is electrons in motion, and these electrons move along a wire. That's the whole idea behind electricity. Now, in order to get those electrons to move along a wire, lots and lots of things have to happen. I have a nice diagram to show you that depicts exactly how electricity is made in the power plant. So we've covered energy carrier. A turbine, sometimes you hear it pronounced turbine, but this turbine is like a fan, like a circular fan, except the blades of the fan are much closer together. And this turbine spins the same way a fan spins. Have you ever done this when you were a little kid? Walk up to a fan that's not turned on and blow into it, and you get those fan blades moving. Well, the same thing happens with the turbine, except it gets spinning very, very fast. Once that turbine gets spinning very, very fast, the electrons move along the wire, and all of these different electrons form our electrical grid. You've probably heard that phrase before because it's interesting. We've had some problems with our electrical grid in the past. Basically, all of our houses are connected by wires, by electricity. And when our wires are all connected, then we're all using electricity at the same time. We're taking electricity from the grid. And it's the power plant that's adding electricity to the grid. It connects all the power plants together, and then all of us end users together. Now, we've pretty well perfected our ability to get electricity to everybody's house. A lot of trial and error, a lot of power plants have been built, and now we're looking for ways to be more efficient about the way we get electricity to everybody's house. One of those ways of being efficient is called a combined cycle power plant. Now, what a combined cycle power plant does is usually a natural gas power plant, and it has two turbines. The natural gas is burned in order to spin the turbine and make electricity that way. But then the waste heat from that process is used to help boil water to make steam, to make more electricity. So that's why this is called a combined cycle power plant. It's using natural gas to make electricity, and it's also using natural gas to make heat that boils water that makes electricity. A typical power plant has a maximum capacity. That is to say, there's only so many electrons it can send along that wire. So that capacity is an important aspect to the grid. And typically a power plant talks about its capacity in terms of megawatts. Don't forget mega. That's a very, very big number. And we, on the other hand, talk about our usage of electricity in terms of kilowatts and kilowatt hours. Of course, kilo is thousands. The actual light bulb is only measured, in individual watts, right? You have a 30-watt bulb, 40-watt bulb, 60-watt bulb. So that gives you an idea. One light bulb is measured in watts, but what you get in your house to run your house is in kilowatts, and what comes out of the power plant is in megawatts. Now this capacity factor here is important for you to recognize, because a power plant can't run at its maximum capacity 24/7. Machines break down, machines have to be serviced, there's lubrication that has to be added to the motors, etc. So a power plant is not operating all of its time. So the capacity factor is something less than 100%. Most power plants have a capacity factor of about 0.9, meaning about 10% of the time it's not functioning. Compare that to some of our renewable energy sources, like wind has a capacity factor of about 0.25. Rather inefficient. That's one of the problems we have with wind. We can't solely depend on wind because it has a lower capacity factor. All right, the last thing on this slide talks about cogeneration. Now I want to spend a minute and a couple of videos to show you what cogeneration is. The best way for you to think of cogeneration is that it's using electricity and heat for more than one thing. That's where the co comes from in cogeneration. Typically how this works is there are a lot of buildings, especially in the north, that operate steam plants. They send hot water through pipes under the ground to every building on the campus. For instance, in our examples here, both of these are college campuses. So there are steam pipes under the ground that connect all the buildings. The steam plant sends boiling hot steam through those pipes to heat exchangers that are in everybody's room. You might have seen these. They're like old-timey in a lot of buildings and in a lot of people's houses. Some people up north still have these heat transfer devices, and we'll see some of those in this video. Well, while they're making the steam and all of these things, these radiators that are being used in the individual rooms, they're producing heat and they're warming the room. These radiators that have steam in them, well, that works great. But what also happens with cogeneration is the steam plants some of that heat that's being used to make the steam is also being used to turn a turbine to make electricity. Before we go to those videos, let me show you the diagram. You've heard me say this before, and you need to know it. You need to memorize this process. At the end of the day, the reason electricity works for us and the reason why it's so great is because we discovered something about 100 years ago. When you move a wire, a copper wire, inside a magnet, electrons move. And the faster you move that wire in a magnetic field, the more electrons go down the wire. So you can do this in a small example in your own house, or we could do it in a big old power plant. So the trick is to get a big ball of wire spinning really fast inside a magnetic field. The faster that big ball of wire spins, the more electrons go down the line. And that's what you're seeing in this picture here. This is a generator. And there's a guy right there. It gives you an idea how big these things are. These are the balls of wire. And then they are coated by magnet. And this thing is humming. There's an axle in here. Can you see this axle? This axle goes through the whole unit, and that axle spins the ball of wire. Spin, 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 spin. Fastest that thing can go, the more electrons run. Now, how do we get that axle, that ball of wire, to spin so fast? Well, that's where the turbine comes in. This is the fan blade thing, and we could blow on it really hard and try to make it spin that way, but what we've learned to do is boil water to make steam. So we send water through a boiler, and that water gets hot from the boiler, and the water evaporates, becomes steam under pressure, and that pressurized steam spins the turbine. The turbine turns a ball of wire inside a magnet, and then you've got yourself electricity. I kind of approach this from the backwards angle, and we have to deal with one other thing. What are we going to use to boil the water? In a lot of our electricity generation, we use coal. And that is the controversy, because coal is a very dirty energy source. A lot of terrible gases come out of the smokestack at a power plant. So this coal comes down the conveyor belt, and it fuels, it produces the heat that boils the water, that makes the steam, that turns a turbine, that turns a ball of wire inside a magnet, and makes electricity. Got it? I hope so. But most of our electricity comes from burning coal. You just need to think about ways that you can make this turbine spin. When it comes to hydroelectric power, we make the turbine spin by dumping millions of gallons of water onto that fan. And that makes that fan spin really fast. When it comes to wind power, we're just using the wind to turn the turbine. The problem is that thing doesn't spin very fast at all, as you can imagine. So if that's not spinning very fast, the ball of wire isn't spinning very fast, and so you're not getting a whole lot of electrons going down the wire. That's why this is our most efficient method. When it comes to nuclear, we're using a nuclear reaction to produce the heat to boil the water. It's all about finding new and better ways to boil that water, to make that turbine spin, so that it can spin a ball of wire inside a magnet. This pie chart here shows you what we use to make our electricity. And you can see 45% of our electricity here in the US comes from coal. About 20% comes from nuclear. We thought that, I think I mentioned this before, we thought that would be much higher by now, but we haven't opened up a new nuclear power plant in many, many years because of the fear. Natural gas burns cleaner than coal. Oil is next. But see, you can see that oil is not a real efficient way to boil the water to make the steam. We'd rather use the oil for transportation. So in some places up in the Northeast, there are furnaces that run on oil, but there are, about 1% of our power plants boil their water to make the steam to turn the turbine using oil. And here are the renewables. You can see we're not much into using renewable energy sources to make our electricity yet. And we'll talk more about that next chapter. Hydroelectric, about 7%. Of course, that's also a renewable energy source. Most coal-burning power plants are about 35% efficient. You heard that guy say that. 35 to 40% efficient. But then it goes way down from there, because that's if they're operating at their maximum capacity. And if they're not operating at their maximum capacity, and they don't operate 24 hours a day, 365 days a year, that 35% efficiency gets even lower. All right, well, that's our little lesson about electricity. And what we're going to do now is focus on each individual fossil fuel, the pros and cons of each. You have got to form a pros and cons table in your mind. Now, as I go through these PowerPoint slides, we will do a pros and cons table. And I think probably each one of these fossil fuels, at least the first three here, each one of them will be their own separate video. So I'm going to end this one now with the electricity, and we'll start the next video by talking about coal.